Welcome to the lesson on Ominos. In this lesson, we will discuss the basic definition of an omino, how to classify them, and how to use them to solve certain problems. Now, an omino is a shape made up of unit squares connected edge to edge. All squares in each omino must have a complete side in common with another square. So as you can see, regardless of how I might take this omino, in this case with 4 unique squares, all the squares are connected. Ominos are named by the number of squares. So 2 would be a domino, which we're very familiar with, the game dominoes. 3 would be a triomino. 4 would be tetramino. 5 pentomino, and 6 hexamino. Now there are a few important concepts to remember when it comes to classifying ominos. Now you determine the type of omino by the number of squares that we discussed, but also by ensuring that each omino is unique and not simply a reflection or rotation of another. Take a look at this particular domino, and look how one square is blue and the other is white. It might be clear to you that I simply turned this domino to make this one, and I flipped that domino to make that one, and then turned this one to make this also one. So at the end of the day, there's only one variation, one type of domino. Let's look at the triominoes. I can have 2 different types of triominoes because I could have the 3 in a row, where these 2 are essentially just flips of each other. And I can have the 2 squares all on adjacent sides by flipping and turning to create different variations, but essentially the same type of triomino. So at the end of the day, there's only 2 types of triominoes. Now when it comes to drawing ominos, let's do a little example on this dot paper plot of doing a tetramino. That would be 4 squares. And let's see how many different tetraminos I can come up with. So I'll start off by drawing 4 squares in a row, making sure they all touch, so that solves as 1. Now if I draw 3 in a row and put one of the squares here on the end, that'd be sufficient for all of those variations. I can draw 3 in a row and put the square off of one of the sides in the middle. That's a 3rd variation. Of course, I can draw a tetramino with 2 on one row, 2 on the other. And then lastly, I can draw all the squares together in a bigger square and get my 5th tetramino. Any others I might come up with will essentially be variations and reflections or rotations of the other. So at the end of the day, I have 5 different types of tetraminos. Now with ominos, I can also consider the fact that they have perimeter and area. Area is as simple as counting the squares apparent in any type of omino, but the perimeter entails counting each exposed side. So with these different triominoes, I can see that I can count 1, 2, and 3 squares, so they each have an area of 3, and counting the exposed sides, 5, 6, 7, 8, would give me a perimeter of 8 for this one, and even though it's a different type of triomino, I still have the difference or a perimeter of 8 with each one. Now this will not be the same for all my types of ominos, so let's take a look at a proof that I can make with an omino. Now ominos can help us in solving proofs, particularly an exhaustive proof, a proof where I justify a claim by showing all the possible examples, exhausting all the examples. So let's use this method of proof by exhaustion to show that the maximum perimeter of a tetramino is 10 units and the minimum is 8. So taking a look at the 5 tetraminos I drew before, I know I only have 5, and most of them have a perimeter of 10, with my bottom one having a perimeter of 8. And of course, they all have an area of 4. They're all tetraminos. But I showed here and was able to demonstrate by showing all 5 that my original statement is indeed true.